Okay, in this video we're going to go through the process of creating a schematic in LTspice and performing a DC sweep simulation and exporting the data into a format that we can then import into Matlab for plotting. We're also going to illustrate the process of making schematics and plots available to use as vector-based graphics figures for incorporating into lab reports. Okay, so the first thing we're going to do is launch LTspice and create a new schematic. And this example is going to be a classical sort of non-inverting amplifier based on an op-amp and a resistive voltage divider. So we're going to need to instance a few components, and so we click on this little AND gate symbol up here in the toolbar to instance a component, and we're going to double click on the circuit sim group, which is what we installed last time from the group of symbols that I've provided for use in the course here. And we're going to need a couple of resistors, so we're going to put down a couple of resistors and right click to cancel, and then we're going to grab an op-amp rails and we'll put that right here. And we're going to need a voltage source, a V source. We're going to need a few of them, maybe one for the power supply, one for the input voltage, and one for a reference voltage. And let's make this one VDD. So I'm right clicking on the instance name here. We can make this one VIN, and we can make this one by right clicking on the V3. We can change this to VREF, and we'll click on the value and change it from V to, let's say, 5 volts for our power supply. And we'll make the nominal voltage for VIN 2.5, the nominal voltage for VREF, again maybe 2.5, in the middle of the single-ended power supply that we're going to have. And let's say that the resistors are going to be, I don't know, 10K. Both of them will be 10K for the time being. So LTspice knows about the typical sort of SI prefixes, although there are a couple of weirdnesses, like for instance, micro is U, the letter U, and milli is M, but mega is not capital M, it's meg, M-E-G. So the MKS prefixes are not case sensitive. That's why there's confusion between meg and mega and milli, and so they disambiguate that by making the prefix for 10 to the 6th MEG, meg. That's a very common trap for people who are new to Spice to fall into. Okay, so we're going to need to wire some things up, and we're going to need to have some power supply, so we're going to need a ground symbol. So this is the ground. So I'm going to put ground, I missed. Put it in these locations. And if I want to move something I've already put down, I can click on this little hand icon, click on it, and then I can move it to where it needs to go. I'm going to use the wiring tool to wire up my feedback connection and my output. And I'm going to connect the rest of this up through what are called net labels. And I'll just move this down a little bit. So you create a net label by clicking on this, and I'm going to need a VIN. I'm going to label the top of this voltage source VIN and the non-inverting input to this op-amp VIN. I'm going to label the output VOUT, and I'm going to label this VREF. Okay, so once I have a net label here, I can actually change what it's called by right-clicking on it and then just typing a new value in here. So you can just copy, not VRED, VREF. Okay, now for the positive power supply, I'm actually going to use a VDD symbol. VDD alt is what I'm going to use here. and this is basically a symbol that is going to be used to denote the connection to the power supply rail. And let's say I want to move this up a little bit, so I'm going to just move this up by drawing a box around it and moving it. Okay, so there's our basic circuit. And we're going to need a couple of more things before we can actually run the simulation. The first is going to be a SPICE directive, which is going to include the engr2420.sub subcircuit definition file that we put into the subfolder last time when we installed all this stuff. Okay, and I usually like to put that down the lower left-hand corner of my schematic. And just let me move this stuff maybe like there. Move that there. And let's save this. So File, Save As, and let's call this Noninv Amp. And we can click on this magnifying glass with the X through it to zoom to the full extent of the window. And to do a DC sweep simulation, we can click on this Run tool up here, and there's a bunch of different types of analyses that LTspice is capable of doing, and they're each in a different tab in this dialog up here. We're going to be doing a DC sweep. Now, this is the kind of simulation that we're going to be doing probably most often in the labs in this class, and so that's what we're illustrating for the time being. But what we have here is a voltage source name, an instance name. We'd like to sweep, let's say, the input, Vin, and we can sweep in a number of different ways. We can do a linear sweep from some starting value to some ending value with some increment that we specify. We can sweep in a logarithmic fashion so that the points are equally spaced on a logarithmic scale, and we can either specify a certain number of points per octave, which is a factor of 2, or per decade, which is a factor of 10, or we can just put in a list of discrete values we'd like it to go through. So we're going to do a linear sweep here. We're going to be plotting a voltage transfer characteristic of our non-inverting amplifier. And let's sweep from 0 to VDD, which is 5 volts. So we're going to go from 0 to 5. And I'm going to make the increment 50 millivolts, 0.05. And that'll give me basically 20 points per volt. And 5 volts times 20 points per volt with an extra one on the end will give me 101 data points. And I think that's a pretty reasonable number to shoot for, because when we make our plots, we're going to want to plot the points as discrete point markers. And if we have data that's too dense, it'll just look like a very thick line and we're not going to be able to see anything. So we'd like the data to be dense enough, but there's still to be some separation between the point markers so we can actually see what's going on. So I usually figure between like maybe 50 and 200 points is probably a good number of points to shoot for in a single plot like this. So we're going to click on OK, and it's basically run the simulation. And so you can see a plot window appears over here, and when we move our cursor around over here in the schematic, we have a voltage probe when we hover over a node, and so we can look at the voltage by clicking on that net somewhere, and it'll plot the voltage on that node as a function of whatever voltage we specified it to sweep. And so you can see here we have a voltage transfer curve here, and if you recall how this sort of amplifier works, the op-amp, if the output is not stuck at one of the rails, must have the two inputs basically very close to each other, because the op-amp has a very, very high gain. And if these two voltages are not very nearly the same, then this voltage will increase or decrease until it hits one of the rails, and then it will get stuck there. And so if the voltage is not stuck at one of the rails in the steady state, that must mean that the two inputs are at the same point. So the op amp will basically be maintaining this inverting input at whatever Vin happens to be. And so the node here at the middle of this two-way voltage divider between Vout and Vref is basically Vin. And so what this amplifier does is it makes the voltage difference between Vin and Vref 1/2 of the difference between Vout and Vref, because the voltage divider is a 1/2 divider ratio. 10K and 10K divides the total voltage drop from here to here in half, and that amount is what appears over R2, and so the gain should be 2, which means that the slope of this line is 2. And so if we look at this, we see that when Vin is equal to Vref, okay, so that the voltage drop across this resistor is 0, Vout should also be Vref. And so we see at 2.5, which is Vref, we get 2.5 on Vout, which is all good. And for every 1 division we go over in Vin, we go up 2 divisions in Vout. And so the gain should be very close to 2. This line looks like it goes straight through those grid intersections, at least at this scale of magnification, which is awesome. And then at some point we hit the rails and we flatten out and we saturate. So that's pretty much what we expect. And we can change various aspects of this plot, like if we wanted to turn the grid off, we could right-click on the plot window and we can view and then uncheck this, and then the grid goes away. So if the grid doesn't happen to appear, it just means that it's not turned on. We can also turn on the discrete point markers if we wanted to here, and that's all good. So if we click on another node, like for instance this inverting input node, we can see that what's going on there. And that comes up here in blue, and we can see that, yay verily, as long as the output voltage is not stuck at one of the rails, what's going on here is that Vin, which is going to be the identity line here, right? If we were to plot Vin on the vertical scale, we'd see Vin versus Vn, which is just the identity line with a slope of 1, that this inverting input, the middle node there, is basically tracking Vn. But then when the output is saturating, it's not moving, which is what you'd expect, because the only thing that's moving this node here, since Vref is constant, is just the output moving. And if the output stops moving, the input's going to stop, or the middle node here is going to stop moving as well. Okay, so that's kind of cool. If I want to delete a trace, like I don't want to see what Vn is, or V minus is doing here, I can right-click on this legend up here, and I can click on delete this trace, and I have just Vout again. So if I want to do this for a different value of Vref, I might right-click over here on the value of Vref, and I might say, well, let me see what it looks like for 1.5 volts. And then I can click on the little running man icon here, and we can see that the curve has shifted over. And when Vn is 1.5, Vout is also 1.5, and this area where the output is changing has shifted over here to the left a little bit. If I change this to 3.5 volts and rerun the simulation, we can see that it moves over to the right, and that when Vn is 3.5, which is Vref, Vout is also 3.5. Okay, so this is behaving exactly like we'd expect. If we wanted to do this voltage transfer characteristic for several values of Vref, we could manually go in and change Vref like I just showed a couple of times, and then rerun the simulation, and then do whatever we need to do with this curve, or with these results on an individual basis. But it would be nice if we could basically do it all sort of at once, and we can do that if we right-click on our simulation command here, and we notice there are several tabs here for specifying what sources we want to sweep. So there's a first source, a second source, and even a third source. So if I wanted to, I could go in here and specify that I want the second source to sweep to be Vref, and I could either make a linear, let's suppose I wanted to make VREF go from 0.5 up to 4.5 in 1 volt increments. So it goes 0.5, 1.5, 2.5, 3.5, and 4.5. Well, I can do that either by using a linear sweep starting at 0.5 and ending at 4.5 with an increment of 0.5, or I could just list out the discrete values by using the list. There aren't that many discrete values, a little more compact just to put the increment here, so that's what we'll do. And so if I click on this and then run the simulation, you see now I have all these values. Actually, I only wanted 1 volt increments, so I can specify that I want fewer increments here by going back here and putting in 1 volt and then rerunning it, and then I'll get a few fewer of these voltage transfer curves. Okay, so that's kind of cool. And if I were to export this data, it would export all 5 runs, which are actually called steps of the simulation. So what it's doing is it's doing the sweep we specified on the first source for a first value of VREF, and then its steps, the next step in the simulation is to rerun that innermost sweep for the next discrete value of VREF, and then it applies the next value of VREF and does the sweep on the first source, and so on. And so when we export the data from this, it's going to export all 5 runs. And we can import that into Matlab, and we'll show you how to do that in just a minute. But suppose I wanted, instead of having different values of a voltage source here, suppose I wanted to do something a little more sophisticated, like trying different values of a resistor or something like that. And I wanted to repeat a simulation for different values of, let's say, oh, I don't know, R1. The way I can do that is to, let me get rid of the second source here. And what I can do is I can take the value R1 of R1, which I had made 10K, and I can define that as a parameter, or in terms of a parameter. And you can actually do all kinds of sophisticated things, like using parameters, which are like variables, effectively, from a programming language. And I can actually do expressions on the values of parameters and things like that. But for now, I'm just going to use a parameter value. So I'm going to just call this R. And the parameter is going to be called R, and I put that in curly braces. And the way I define a parameter is by putting another spice directive in the schematic here. And I'm going to say .param for parameter R equals 10K. So I'm going to give it a nominal value here, which was the same as my initial nominal value. And just let me move this DC sweep over a little bit. And now, if I were to run the simulation again, oh, this is 3.5, haha. Let me put this back at 2.5. So I'm back here to my initial simulation with VREF at 2.5, and now R is going to have its nominal value of 10K, which I specified down here in this parameter definition. But suppose I wanted to rerun the simulation for, let's say, I don't know, 4 or 5 different values of R. And that'll, of course, change the slope of this line, which is the gain of the amplifier, because the gain of this amplifier configuration is basically the reciprocal of the voltage divider ratio here between V out and V minus, which is going to be R1 plus R2 over R2, or 1 plus R1 over R2. And so the way that I repeat a simulation that I've specified for different values of a parameter is by using yet another directive, which is called a .step directive. And the thing I want to step here is a parameter R, and I'm going to specify it as a list of values. And I'm going to say do 1K, 3K, 10K, and oh, let's say 30K. Okay, so the list of values here is separated by spaces, and roughly 3 on a logarithmic scale is halfway between 1 and 10, because the square root of 10 is like 3.16, so 3 is close enough. So if I do that and I put this down here and I run it, you'll see now that I have 4 simulations here, 4 different voltage transfer characteristics, and the slope of the line has changed. So this is the 1K, this is the 3K, this is the, I'm sorry, this is, see, this would be, oh, this would be the 30K, the 10K, the 3K, and the 1K. Because in the limit, as R gets smaller and smaller, this just becomes a unity gain follower, and we approach the identity line. So yeah, that's right. It's going in the other direction. This is the lowest resistor, and then this is the highest resistor. Okay, so that's cool. Now, suppose I wanted to get this data into Matlab so I could do some things like fit a straight line to these voltage transfer curves and label the axes and do all that good stuff. Superimpose a fit line on here to make a figure. How do I do that? So let me just save this here. And if I click on the plot window, what I can do is I can go up here to the file menu and I can export the data as a text file. And now whatever I have shown over here in the window will show up as highlighted variables or something that I can put in my export. And so that's good. If I just want what I've got shown over here to go out, I don't have to do anything. I can basically just give the thing a name and click on OK, and it saves it as a text file with the same name as the schematic by default, so that's fine. And I'm going to click on OK, and for the time being I'm going to lower this, and then I'm going to open up my Documents folder, and it's saved. I saved this in my sort of LTspice XVII folder, which is not a bad place to put your stuff. And there's the text file. And I think what I'm going to do is I'm going to move it over to my Matlab folder, just so that it's conveniently located for getting into Matlab. So I'm going to just copy that over, or move it over to my Matlab folder, and I'm going to run Matlab. There's Matlab. And now what I'm going to do is I'm going to run LTspice, which was one of the 2 Matlab functions that we installed last time. So LTspice, and the name of the file is noninvamp.txt, I believe. Let's just see if that is over here. Yep. Okay, so if I hit return, you'll see over here in the workspace I now have three MATLAB variables here. One is R, which was the parameter we had changed in our simulations. And then we have Vn, which is a row vector of 1 row by 101 columns. So that's the 101 values of Vn. And then Vout is a matrix, 4 rows by 101 columns, and so each row in this matrix corresponds to one of the simulation steps. So if I look at the values of R, you can see that the values of R are the ones that the succession of parameter values that we specified, 1K, 3K, 10K, 30K. And the rows in Vout correspond to the values, simulations done with the values of R that are in the order that are in this R parameter here, so our R vector. And so I can just plot Vn, Vout, just plot it as discrete point markers, and there's our voltage transfer characteristics. And we can do stuff with this. Suppose we wanted to, I don't know, fit a straight line to the 10K one, which is going to be the 3rd index here. and plot that along with our voltage transfer characteristics. So one way we could do that is use polyfit. We'd have to basically slice out the values of Vn, or the indices of Vn, and the particular row in Vout that we would like, that would be reasonably considered to be part of that place in the curve where it's not saturated. Or we could maybe use a GUI in the Matlab curve fitting toolbox to graphically select what part of the curve we want to fit a straight line to. And that's fine. If you want to do that, that's totally fine. I have provided for you this line fit function. So if we type help line fit, you can see what it's doing. But what it does is it takes an x vector and a y vector, and then a small numerical parameter called epsilon, which is a small number. Typical values are in the range of, let's say, something times 10 to the minus 4 to something times 10 to the minus 3. And what it does is it tries to fit a straight line to the x and y vectors, or a part of the x and y vectors, to within an r squared value of 1 minus epsilon. Now, a perfect straight line fit would be an r squared value of 1. And so by specifying some epsilon value that's small, we're basically saying we were looking for a place in the data where the straight line fit has a goodness of fit of at least 1 minus epsilon, and it's at least got 10 points in a row where that fit is done. It basically tries to fit at least in this goodness of fit category for as many points as possible, and it latches onto the part that has the steepest slope. And so it will tell you, it basically returns the slope and the intercept, the number of points that it used for the fit, and the first index and the last index. So what I can do here is I can say, let's say first, last, M, B, N equals line fit, and I'm going to do Vn for the x values and V out. Let's see, I want the third row. I said I want the 10K case, comma colon, to slice out the third row of the matrix. And I'm going to use let's use 5e minus 4 for our epsilon parameter. Okay, so you can see here that it picked the 28th index to the 79th index, so 52 points. And it returned a slope of 1.974, which is pretty close to 2, and a y-intercept of minus 2.5 volts. So if we want to plot, so the voltage transfer curves are already up there. Or no, I got rid of the figure window. Okay, so let's go back and plot Vn and Vout, and we'll do hold on. And now we're going to plot Vn and then M times Vn plus B, which is our model for the 10K voltage transfer curve. We're going to label that, or we're going to render that as a straight line in black, a solid line in black, and let's look and see what that looks like. So here, this yellow set of dots is the simulated data, and this is the straight line fit. And you can see it's done a pretty good job. Now, when you make a plot for the labs in this class, I want you, as a matter of principle, to basically make the data, the simulated data, take up most of the vertical real estate. I'm not interested in seeing this extrapolated straight line fit and then squash the data so I can't see what's going on. I'm really interested in having you zoom in on the actual data to see what's going on here. So you could do that with the GUI. I like to do it with the axis command. So the axis command basically returns the limits, the x limits and the y limits that it's currently using for the current plot. And if you pass it a 4 vector, it changes it to be that. So I want 0 to 5 and 0 to 5 on both x and y. So if I do that and I flip back over to the curve, you can see now I'm zoomed in on the voltage transfer curves like I was before. You can see it's a pretty nice fit. I might have been able to exclude some of the data where it's starting to saturate and maybe get a slightly better fit, because it looks like the fit is a little bit low here and a little bit high here, but it's probably good enough. I would do that by tightening up my tolerance a little bit, so instead of 5e minus 4 for epsilon, I might use like 1e minus 4 and try that. But this is good enough for our purposes here. You always want to label your axes, so you can use X label and VN and put units on it. Y label, V out, and put units on it. So there's our beautiful figure. Maybe we want to turn the grid on. Maybe you want to put a legend in. Whatever. Whatever you need to do, you can do it. And now you have this figure and you want to import it into, let's say, a Word document for your lab report. There are a number of different ways you can do that. What I would prefer that you not do is to use a raster image format, like a JPEG or a PNG file, or do a screen grab. I would very much prefer that you use a vector-based image format of some kind, so that the files aren't super large. So in order to get good resolution, you have to have a lot of pixels in a rasterized image format, and that creates PDF files that have these enormous figures, which turn into multiple tens of megabytes, and it's a pain to deal with those kinds of files. So if you wouldn't mind, I would very much appreciate you working to use vector-based image formats. And on Windows, a very convenient one, it turns out, is the enhanced Windows meta file. And so I want to just show you how to generate an enhanced Windows meta file from Matlab plot, and also from LTspice how to generate a schematic as an enhanced meta file. So what we would do is to use the print command. So print, if you do help print, it gives you a nice help comment, and it shows here the full list of file formats is documented here. So if I click on that, you'll find in the MATLAB help that on the Windows platform there is I think it's dmeta. So -dmeta is an enhanced Windows meta file, and it's got a .emf extension. Okay, so for Windows, I think that's probably your best bet. You can also do an EPS file, probably an encapsulated PostScript file, maybe a PDF file, but it would be good to use some sort of vector-based image format. So if I do print -dmeta and then say noninv amp VTC .emf, and I go back out to my Matlab directory. Let's see, where's my Matlab folder here? There it is. If I double click on it, I get it opening up in Paint as a preview here. You can directly load that into Adobe Illustrator if you want to annotate it in some way, or edit it, or convert it to a different format. You can also incorporate it directly into a Microsoft Word document. So let me close down MATLAB, and let's go back over to LTspice and make where's my LTspice window? Okay, so suppose I wanted to write out this schematic in a format that I can put into Word, so an enhanced meta file. So I go up here to the Tools menu with this window selected, and I go to Write Image to EMF file. And I could call this noninv schematic, let's say, and save that. And then if I go to my LTspice directory, you can see I now have my schematic. Okay. And so let me fire up Word. Now I've only got an old version of Word on this computer. I'm sure this is going to work the same way with the new Word or Office 360 or whatever it is. So I start up a new blank document. I can go Insert, Picture, and if I go here, I get my schematic. And if I wanted to, I could make this smaller. Let's make it a little bit smaller. And then go down here, and if I wanted to insert, say, the voltage transfer curve, I can grab that here from there. And so I haven't put figure captions. In general, you will want to put figure captions in. You will want to, reference the figure by the caption. You may want to make them floating bodies or whatever. But I just wanted to illustrate that when I put this into a PDF file, I could print to a PDF file. Here I'm using Adobe PDF as my printer. And let me call this noninv.amp.pdf, and this is going to go on my desktop. I don't like the Windows PDF preview. I'm going to open this with Acrobat. So you can see here that I can zoom in on this and it's beautiful at any resolution. I can also zoom in as far as I'd like on this plot, and I can make out exactly what's going on. It's not pixelated, it's beautiful. And if I go out here and look at how big the file is, it's tiny. It's like 80K, not 3 megabytes. So please, 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 when you're making your figures for your lab reports, use a raster. Don't use a raster-based image format. Use a vector graphics-based image format. Anyway, so that's a few things about using LTspice and importing the data into Matlab, doing some curve fits, making figures, and things like that. We'll be looking at some other features of LTspice as we need them, developing those, but that's it for now. Thanks for watching.